So I'm going to invite Gaurav on stage, who is uh, going to do a small fireside chat with Yann. Gaurav not only heads AI for Reliance, but is a fairly well-respected scientist in his own right. He's IIT Chennai BTech, and more importantly, a PhD from University of Maryland. And uh, other than working in Google and Yahoo, where I think, Sharad, it overlapped with you a little bit probably. No, not really. Yeah, you survived. Very good. And Ola. But importantly, he wrote a neural network at 24 years of age, and you know, and that's, I think, makes all of us. Jan, if you remember, it was called an expert system. You remember there was a prologue, the language that we wrote on a machine, and it was kept only on the. So I really like the way Gaurav and I talk about those days. But anyway, he's much younger to me. Jan, before I hand it over to Gaurav to ask you some questions, if you want to ask Jan some questions, there is a QR code, I think, somewhere available on the chairs or wherever. Yeah, there it is. Sure, thank you. And you can do that scan and ask your questions, and I think it would reach Gaurav real time. And as I end, Jan, I want to make sure you know that there's a lot of fans in this crowd for you. There are people who've traveled across this country to be here today, and at least 40% of this crowd is not from Delhi, and they've come all over India because you have that kind of a fan following. So Gaurav, over to you.
Yeah, thanks, Jess. I'll start with, we have been working with Sunil and Prachi from Meta for, to organize this event. And Sunil was very worried, actually. The whole thing about this QR code is, Yann is outspoken, as we all know. If those of us who have, and it's not new, actually. I think even before Twitter, I think he used to be the same way. He has not changed a bit ever since I have been following him since my PhD days. And Sunil was very worried. And he's like, when I told him, yeah, Yann is outspoken, we'll have fun. He's like, no way. He only wears the Meta hat, and he has to be careful. So hence, please, if you want to ask questions, I have to respect Sunil. He has been kind enough to have us host Yann. So please, fill the form, and it will reach me, and I'll be open. Like, as long as it's not obnoxious, I'll ask that. And yeah, Sunil is trusting me on that. So first question, Yann, I think, recently, in the talk you gave at IIT Madras, you mentioned LLMs, as they exist today, they're sort of plateauing. So what next at a very high level? I know it's a very loaded question, and I'll probably break it down in further questions, but what next? Like the academic Yann, without revealing anything what Meta is confidentially doing, what do you think is next?
Well, that's my favorite topic, really. So yeah, LLM are great, but they are very limited in their capabilities, particularly in abilities to understand the physical world, which they don't. Ability to have some sort of persistent memory or working memory, and then ability to reason and plan. You can add hacks, essentially. I apologize to Mano. They're not totally hacks, but this is what his team is working on to improve LLMs at the moment. So hacks to kind of get system to maybe understand images and reason just a little bit and use tools and plan how to use tools. But in the end, it's not a perfectly satisfying solution. So one thing that we're working on is a program that we call Advanced Machine Intelligence, AMI. At Meta, we pronounce it AMI, because there's a lot of French-speaking people, and AMI means friend in French. So we think that's appropriate. We prefer this AMI acronym to AGI, the reason being that human intelligence is not general at all, it's very specialized. And so calling human-level intelligence general intelligence is complete nonsense. That ship has sailed, unfortunately, but we call it AMI. And the idea of AMI is, without being too technical, the way you train a natural language understanding system is using self-supervised learning, and self-supervised learning basically consists in training a system to fill in the blanks, right? You take a piece of text, you corrupt it in some ways, remove some of the words, replace them by blank markers, and you train a big neural net to predict the words that are missing. There's a special case of this, which is LLMs or autoregressive LLMs. And there you don't need to corrupt the input. You just need to show the input, but you construct the network in such a way that to predict one output, it can only look at the inputs to the left of it, okay? So effectively, you're training the system to predict the next word in the text. And in doing so, then you can use the system to just generate text, right? You have it produce a word, and then you shift that word into the input, and now you can produce a second word, shift that into the input, and now you can produce a third word, etc. That's called autoregressive prediction, and that's what LLMs are based on. Now, the downside of this is that those systems, so there's a number of downsides. The first thing is that those systems devote a fixed amount of computation per token. So you ask them a complex question. If the answer is yes or no, you will spend the exact amount of, same amount of computation, regardless of whether the question is hard or simple. And that doesn't make any sense. We tend to devote more resources to complex questions than simple ones. So the tricks that people have found is that they artificially trick the LLM to produce more tokens, so that it's going to devote more computation to the problem. That's called chain of thoughts. So you ask the system to explain why it's producing the answer. You don't just ask it yes or no. But that's a trick. It's a hack. Now, here is the issue. When you train a system to predict the next word in a text, or the next token, which is really a subword unit, you cannot possibly predict exactly which word will follow in a text. And so you train the system to not produce a single word, but produce a distribution of all possible words, right? And that's a big vector of numbers between 0 and 1 that sum to 1, whose size is the number of possible tokens or possible words in your dictionary. And that allows the system to basically be trained in the presence of uncertainty, and then you can use the system to not predict a single string of words, but multiple strings of words by sampling from that distribution that it produces. Here is the thing. Now, there is an old idea that goes back 15 years, so it's not a new idea. I've been working on this for at least 15 years, and it's the idea of using the same principle of self-supervised learning to train a system to understand the physical world. Take a video, corrupt it in some ways, and then train some big neural net to fill in the blanks, predict what's missing in the video. So for example, take a 2-second video, show the first half second, mask the second half, for the first half, 1 second, and do not show the continuation of that video to that system, and train the system to predict the second half of the video. We've tried doing this for 15 years, and it basically doesn't give you any interesting result. The system cannot predict what's going to happen in the video because there is an infinite number of plausible things that could happen in the video that you cannot possibly predict. If I take a video of this crowd here, I start from here and I move the camera and I stop here, and I ask the system what's going to happen next in the video, it's going to predict that the camera is going to keep moving, that this is a room, there's probably going to be a wall at some point, there's probably going to be people sitting on this side of the room, and everything. There is no way the prediction can predict what every one of you will look like. There's no way it can predict the texture of the ground or the texture of the wood panels on the walls, or where the wall is, how big the room is. You know, there's lots of things you cannot predict in the world with partial information. And so when you train a system to predict how a video continues, the best thing you can do is predict some sort of average of all the plausible futures, and that's a blurry image. So it doesn't work. So of course, the solution to this is let's not predict a single image or a single set of videos. Let's predict a probability distribution over video frames. And the problem is we don't know how to do this. It's actually a mathematically intractable problem that not just computer scientists, but also physicists and statisticians have struggled with for decades. And it's basically not solvable. And so the solution to this, so I struggled with this problem for years. And a few years ago, we discovered a way to get around that problem by building on an old idea, actually, called joint embedding architecture. So what is a joint embedding architecture? It means let's not try to predict all the pixels in the videos that are missing. Let's find an abstract representation of the video that eliminates a lot of irrelevant information that we cannot predict anyway, and then let's do the prediction in the abstract representation space where you can make predictions. And And that's called a Joint Embedding Predictive Architecture, JEPA, JEPA. All the projects I'm working on at the moment at FAIR with my colleagues are based on this idea. And I'll give you why it's a very fundamental idea and why it's really important. Let's take an example of a very complex object. Let's say Jupiter. Jupiter is a planet. It's a very big planet. It's got enormous amounts of information that we can gather about Jupiter. But if what we're interested in is predict the trajectory of Jupiter, the representation of Jupiter that we need is very simple. We don't need to know how big it is. We don't need to know the density, the composition, the temperature. None of that matters. The only thing we need to know is 6 numbers, 3 positions, 3 velocities. And we can predict the trajectory of Jupiter for centuries, assuming Jupiter is light compared to the sun, okay? Which it is. And so what that tells you is that to the problem of prediction is a problem of learning good representations of the world that eliminate the stuff that you cannot predict and keep the stuff that you can predict. And this is what the JEPA architectures are designed to do. This is going to be, I think, the blueprint for the next generation of AI systems. And what we can build from this JEPA architecture is something I call, I'm not the only one to call them that way, but which are called world models. So what is a world model? A world model is a sort of mental model of the world, which from the state of the world at time t and an action that you imagine taking, can you predict the state of the world at time t plus 1? If you have such a mental model of the world, then that means that you can, in your mind, imagine the result of a sequence of actions and see if that sequence of actions will result in a satisfying a task that you want to accomplish. I don't know, filling up a glass with water, right? If I want to fill up this glass with water, I need to take up the glass, turn it around, pick up the water bottle, open it, and then pour water, right? That's a sequence of action that's fairly complicated. Of course, we're used to doing this kind of gesture, so we don't need to plan. We're used to just doing it without thinking. But most of the problems that you do for the first time, you have to kind of plan the sequence of actions to accomplish them. So that's called planning. You can reduce every reasoning problem as a very similar problem of finding a sequence of actions or symbols that satisfy a certain condition which characterizes whether you accomplish the task or not. And so this principle of inference by optimization, so the problem you're solving when you do this is an optimization problem. You have an objective function that says whether your task has been accomplished. You have a world model that predicts whether the state of the world will be the one that you want. And then you have a sequence of actions and you optimize, you search for a sequence of actions that will minimize that objective function that you set up. So that's inference by optimization. This is intrinsically more powerful computationally than inference by forward propagation through a bunch of layers in the neural net, which is what LLMs do. Okay, so perhaps with this kind of architecture, we'll have a way of building machines that can reason, that can plan, that have mental models of the world. Perhaps those models will be hierarchical. That's another story. And maybe we'll have a path towards systems that can learn how the world works from video, have common sense, can reason and plan, and maybe at some point can reach human-level intelligence. Our plan for this, which is an optimistic plan, is that we might be able to reach kind of a good system to accomplish all those things within 5 to 6 years, maybe 6 to 7, and perhaps be on a path towards perhaps building human-level systems of that type within a decade. That's what the FAIR organization, Fundamental AI Research Organization at Meta, that's its mission. We're working on other things that are more applied too, but that's the main mission. And Mano, in the back of the room, is crossing his fingers that at some point we're going to succeed, and Llama 5 or 6, or maybe 7, I don't know, is going to be based on this new idea, and we're going to be able to deploy those intelligent systems on every smartphone and smart glasses, and everyone in the world is going to be able to talk to an intelligent AI assistant, which might be smarter than themselves, but will help everyone in our daily lives. And perhaps this will have the effect of amplifying human intelligence as a whole and lift humanity to the next level. All right? How is that for a cosmic conclusion?
Thank you. Thank you. So on that note, I'll ask something little, I know you're not a fan of autoregressive models anymore, at least taking us to AGI or AMI, as you call it. Recently, I'm sure you would have seen it, like recently, I think, or a few months ago, Jensen was having a fireside chat with Ilya, and I think it became viral. So he gave the example why he believes next token prediction is and they still call it AGI, so will lead to AGI. And the example was, like if you're reading a sort of a suspense novel, by the end of it, you as a human, like when the name is about to be revealed, you are sort of guessing it. What is your take on it? Like I have my own personal opinion, but here we are, to hear your opinion on this.
So I think he's completely wrong. I mean, I love Ilya. He's a brilliant researcher. He's brought a lot to the table. He's made some really major contributions. But on this, I think he's completely wrong. We're not going to get to human-level AI by just scaling up LLMs and then training them on more data, and then hacking it so that we have a little bit of reasoning and a little bit of image understanding. I mean, it's useful to do all those things in the short term. There's no question, and we're working on it, and Manu is working on it, and his team are working on it. This is what you're going to see in Llama 4 at some point. We're not going to tell you when. But clearly that's something very valuable in the short term. But long term, if we want to reach human-level intelligence, we need new paradigms, perhaps of the type that I just described, using those JEPA architectures, this objective-driven architecture of systems that really plan their answer and their actions. And reasonable people can disagree on this. Ilya and our common mentor, Jeff Hinton, Jeff believes that LLMs actually have subjective experience. I really don't believe that's the case at all. So this idea that somehow we're going to be able to just scale up and we need $1 trillion investment in computing infrastructure and collecting all the data in the world, and somehow human-level intelligence will emerge from LLM, I just do not believe that's the case. And there is a very long history in the history of AI of people embracing a new paradigm and then thinking that the problem is solved. That has been a repeated event in the history of AI since the 1950s. One of the first sort of classical AI system in the 1950s was the work by the legendary Newell and Simon, both Turing Awards, for their contribution to AI. And they built an AI system that they very humbly called the general problem solver, 1956. Okay? They thought that reasoning was reducible to just a search for a solution, basically the process I described. You have a cost function or an objective function, and you have a space of possible configurations or solution. You just search through that space for one that satisfies the condition, and your problem is solved. An example, the traveling salesman problem. You have a list of cities, and you have to find the circuit between those cities that is the shortest. There's only a finite number of possible trajectories, in factorial n. You just search through them and find the best one. You want to play chess, just imagine all the moves that you can make, and then all the moves that the opponent can make, and then all the moves that you can make on top of this. And you have this tree of possibilities. You just go through that tree and find the one that is most likely to lead you to a victory, right? That's how chess playing systems were designed. It turns out all of the problems you can formulate this way are essentially intractable. They all lead to exponential growth. And so that general problem solver couldn't really solve any interesting problem, okay? But that led to a branch of AI, which we now call good old-fashioned AI, basically heuristic programming or logic reasoning, rule-based system. The other branch of AI was based on learning the perceptron and neural nets. It led to neural nets. But those people, when they discovered those new principles, the perceptron was going to lead to intelligent machines. That was false. The general problem solver was going to lead to intelligent machines. That was false. Logical reasoning, Prolog, expert systems was going to lead to a whole industry and intelligent machines. That was false. then neural nets with backpropagation in the 1980s and 90s was going to lead to intelligent machines. That was also false. It was not entirely false because basically what we're doing now is a continuation of it. But it was too early. And so there's a long history of this, of young people who are very enthusiastic about their own production and saying, that's it, we've got the problem solved. And then older people who say, like, wait a minute, I've seen this before. Okay, and I'm older, okay. But I have a plan. I know how to get there. I'm not telling people, there are other people in there who say, like, we're just never going to get there. Like, we tried for 50 years and nothing worked. And, yeah, we're making progress, but it's like toys. And, we're just going to build applications. Let's not even try to build intelligent machines. But we have a plan.
Cool. So, I was listening to one of your older talks with one of the French institutes. You mentioned something like theoretical streetlight effect. Like too much of worrying about mathematical correctness, it restricts innovation. Right?
Yeah.
And you mentioned like engineering comes first. That's like coming up with ideas is engineering. And theory kind of makes those ideas more efficient in some way over time. Do you think some of these sort of over-exuberance on potentially misguided ideas or whatever, like I'm just taking the leaf from where you left. Is it having that, it's not theoretical, but it's having that streetlight effect where we are spending too much time, too much energy, too much money, which is real, on this, and it will actually, slow us down in true sort of, innovation we are supposed to make here.
So I think the field went from one extreme to another. So there was certainly irrational exuberance in the 1980s and 90s about the potential applications of neural nets. It turned out to be a lot more difficult than we thought because we needed large data sets, powerful computers that we didn't have at that time. What we also needed is a way for scientists to share experience through open source code. It turned out implementing neural nets in the 1980s and 90s was really a major undertaking, and people didn't share open source code, so there was no kind of common, platforms that, there was no Python, right? There was no common operating system that everyone was using, different types of computers. Code was not portable. Floating point arithmetics was really slow unless you had really expensive computers. And so there was no way that the field could progress, mostly because of, there was no good way to exchange code. And the idea that even universities, but certainly industry was going to make their code available for free to everyone, that was completely out of the question in the 1990s. And so the field couldn't take off because of lack of data, computing resources, and the ability to share code and tricks. Because to train neural nets, you need a lot of tricks that are hidden in the code, right? It's not, you can't just reproduce it from a paper. You have to download the code and see, oh, that's how they do the scheduling for the learning rate or whatever. So the field kind of died in the 90s because few people were willing to invest the resources to build a deep learning neural net training system. I spent that effort for a year or two during my postdoc. Jeff Hinton had the impression I was not doing any work. I was actually hacking, okay? And then when I got at Bell Labs, we kind of finished that thing, and that's what enabled us to do convolutional net. Convolutional nets are not a particularly sort of revolutionary concept. So other people had similar ideas before, but just implementing it and making it work required basically a year of investment in writing software. But once we had that piece of software, it was called SN. It became Lush in the end. It became open source years later. That gave us superpowers. If you build your own tools, it gives you superpowers and allows you to produce things that other people can. Okay, we've done this also at Meta with PyTorch. And other tools that we open source, so we enabled other people to profit from our advances. But really, what was missing was this communication, computation, and data. And so interest in those techniques kind of died in the 90s, and people found themselves excuses for not working on neural nets and for working on simpler methods like logistic regression, Bayesian inference, boosting, classification trees, XGBoost, things of that type. And the excuse was, oh, neural nets, they're too complicated. The only people who can train them is Yann LeCun and maybe a couple other guys, but that's it. And yeah, they work really well on recognizing handwriting, but if you have a small data set, they don't work that well. They need a lot of data to train, and so they're not really practical for many things. Yeah, he got really good results on MNIST, but MNIST is just one problem. And look, with supervector machine, we can get almost the same good result by cheating a little bit. So, there was a lot of kind of dismissal of evidence and then theoretical arguments, and the theoretical arguments is, I can approximate any input-output function I want with one layer of similarity detection and then called kernels, and then a linear combination on top of it. That's just a two-layer system where the first layer is basically fixed and only the second layer is trained. It's very simple. The cost function is convex. I can prove that it can work. I have a generalization bound. I can have this small piece of C code that I can just run, turn the crank on, and it's going to converge every time. I don't need to tweak learning rates, blah, blah, blah. And so those methods took over, and people found theoretical excuses for dismissing neural nets, saying it's non-convex, we don't have proofs that it works, blah, blah, blah. And so that's an example of losing your keys somewhere on the street and looking for them under the street light because that's where the light is, even though you know that the keys are someplace else.
Thank you, Yann. So now I'll move on to the audience questions. So it is Subhashish from AI Foundry wants to know, who will create the fair equivalent in India? Will Meta do it in India? What they did in Paris?
Okay, there's a slight sad thing, which is Meta has gone through a phase since late 2022 of essentially kind of shrinking a little bit, eliminating a bit of excessive growth that had occurred during COVID because there was a huge demand for the services of Meta during COVID. And so Meta hired a lot of people and then realized, okay, that was temporary, now we have to fire people. And so that's not a good time to open a new research lab somewhere, okay? Then Meta is very much centered on, it's very much a Silicon Valley-centric company. We have labs in New York, in Montreal, in Seattle, in Paris, in London, in Tel Aviv, the biggest one being Paris, New York, and Menlo Park. So it's somewhat decentralized. For research, engineering is much less decentralized. We only have big engineering centers in a handful of places. And so the company, as a philosophy, doesn't like to kind of delocalize, disseminate too much. Certainly not in periods where it's getting rid of personnel. So for the last 2 years, basically the question was not even raised. But it might change in the future, and it might become possible to open new labs in other locations, potentially in India, potentially in other countries. We don't have any labs in Asia. We don't have any engineering offices outside of Europe and North America. So it may happen at some point. I think the company is exploring those possibilities on a regular basis, but there's nothing to announce. Okay, so that's for Meta. Yeah. Now, what I think India should do is perhaps change the culture of industry a little bit, similar to the story I was telling about France, so that large companies in India that are highly profitable would set up ambitious research lab and then give career opportunities for young, ambitious scientists, perhaps cause young scientists from India to come back to find jobs here. Well, you did this. And you did this too. And come back, perhaps. But that means career opportunities in India for scientists, ambitious researchers outside of academia, in industry. That requires investment, a willingness to take risks, a willingness to do open research and development, and a change of culture, essentially.
Cool. I'll go to the next question. It is asked by Jaskaran Singh Dubvers. You have mentioned probably in one of your talks that we will reach human level AI in 5 to 10 years. I think the question is, do you think we'll be able to understand neural networks before that and come up with a robust theory of DL? I don't know, it is like, yeah, sort of similar on the lines of the question I asked you. I mean, I know your answer, but I think people probably want to.
Yeah, I mean, there is quite a lot of theory being done in the context of neural net to kind of understand how they work why they work so well, even though they break the basic textbook, statistics that you see. Every textbook in statistics would tell you, well, you don't want too many parameters in a statistical estimation models because it will overfit your data and not extrapolate properly. And that turns out to be largely true, except for neural nets. Neural nets somehow, you give them a huge number of parameters and they still work and they still generalize. And from the theoretical point of view, that was one of the excuses that people used to say neural nets will never work. That turns out to be completely false, and the theoreticians had to revise the theory and come up with concepts like double descent and things like this, and sort of implicit regularization and stuff like that, right? So that's something. There's a point that I wanted to make in response to the previous question, but it's relevant to this one. It's the fact that in the history of science and technology, it is quite the case quite often that the creation of engineering artifact preceded the theory that explained why it worked and what the limitations of it were. A good example for this is the steam engine. The steam engine was invented in the late 18th century, but the theory for it, thermodynamics, didn't come up until about a century later. Carnot cycle, entropy, things like that didn't come until the 19th century. Similarly for airplanes. I mean, aerodynamics was kind of a field, but not really in the early 20th century. But tinkerers figured out, how you build an airfoil, and they built wind tunnels and stuff like that. The Wright brothers and Clément Ader and Otto Lilienthal, a bunch of people like that, and experimented with flying machines. And then eventually, there was a whole theory about, aerodynamics of wings and blah, 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 that developed from it. And so, the telescope was invented and the lens was invented before the theory of optics was figured out by Newton. Of course, there are other people who figured this out in Arab countries, in the Arab world in the Middle Ages, but that was unknown in the West. So this is very common. And to some extent, deep learning is seen as a bit of a alchemy, because a lot of it is empirical. You search, you have some intuition about something that might work, you try it out, and it doesn't work, and then you try something else, and it kind of works, and you're surprised by how well it works, and then you try to kind of figure out why it works. And so a lot of it is very empirical. But there is some theory, and there is a need for more theory. I've been trying for a couple of decades now to attract physicists and applied mathematicians to the problem of explaining why deep learning works so well.
So going to next, there are a couple of questions around regulation. I'll skip them because Sunil is my friend.
Okay, I have one answer to this known question. Okay. Do not regulate open source AI platform out of existence. Okay, and there is a lot of mistakes that the regulators can do that will perhaps deliberately or involuntarily make it risky to deploy open source AI platforms, and basically will kill the entire field. It will kill the ecosystem. Everybody in India that I talk to is using Llama in some form. We're talking about hundreds of startups and large companies like Infosys. They're using this, and they're using Llama to serve their customers. You make open source difficult or risky, that entire industry dies the next day. Okay?
Yeah, it will lead to more consolidation, clearly. It's about synthetic data. So actually, I had a question on synthetic data, so I'll ask that before I'll take this question. What's your take on synthetic data? There are a lot of startups that came up, like boutique startups, and a lot of money, again, was poured into it, which has changed in recent times, I think. So again, I would love to know the real Jan's reaction to is synthetic data, and because my take is like synthetic is there's nothing synthetic. It is learned from the natural data. I mean, it is not random. So what do you think? Does it help? Should
Okay.
people be investing in it?
So the first thing is that to some extent, all data that LLMs is trained on is synthetic. It's human produced. Okay, so it is synthetic.
Okay.
But then there is kind of naturally synthetic data, right? Text that people produce for other reasons, not for training LLMs. So that is, you collect data from the public internet, you license some of it from publishers and things like that, and then you clean it up because most of it is garbage. And then that's your pre-training data. You train your LLM with this, and then your LLM doesn't work. You have to fine-tune it to answer questions, to solve problems, blah, blah, blah. And that requires semi-synthetic data. That requires hiring a lot of people and playing with the system, and then training it to produce correct answer, rating the answers that it produces, etc. Sometimes you can do this semi-automatically. So for example, if you have a code generation system, and you ask it to write a function that produces a particular result, you can check if the code works, more or less automatically, right? So the system can adjust itself to produce code that actually works. Then other type of synthetic data. So if you can have very simple simulated worlds where simple events occur, like Yann goes to the table and picks up the glass, and then picks up the bottle. Okay, now you ask the question, how many glasses are on the table? Okay, there's only one left because one of them is not on the table anymore. This kind of situation that will teach a system that an object can be in two places at the same time, that when you take one object away from a location, then there is n-1 left on that location if there were n of them to start with. All of those really basic things that we take for granted need to be trained by a system. The basic idea of logical inference has to be trained, and for this you can use synthetic data. So I think there's a bright future. Now, that said, if you imagine a future where most of the data, most of the text on the internet is generated by AI systems, and you keep training those AI systems with data generated by other AI systems, the system will collapse. Okay, and we have experiments on this. We have a paper that came out of Fair Paris recently that shows that this is not going to work, right? We have to be careful about this.
And I think as a community, we are getting there in our hunger for data.
Yeah.
Because soon, most of the data on internet will be, LLM generated in some ways. Or
right, but you can use data to basically simulate virtual worlds where systems can learn a lot of things, about the structure of the world. And ultimately, you don't want to train systems purely on text. You want to train them on video using perhaps the JPA architecture I was talking about. There is a set of numbers I like to quote, which is that a typical LLM today is trained on 20 trillion tokens. Each token is about 3 bytes, so the total amount of data is 10 to the 13 bytes. Okay, I'm going to round this up to 10 to the 14 bytes. This is the entirety of all the public text available on the internet. It would take us, any of us, several 100,000 years to read through it. Okay, enormous amounts of data. That said, a 4-year-old has been awake a total of 16,000 hours. Every second of wake time, a child or a baby perceives, gets on the order of 2 megabytes per second to the visual cortex through the optic nerve. We have 2 million optic nerve fibers, each carrying about a byte per second, so that's 2 megabytes per second. Do the arithmetics for 16,000 hours, and within 4 years, a child has seen as much data as the biggest LLM, about 10 to the 14 bytes. So it's not the same kind of highly structured abstract data, of course. It's low-level data about how the world works. But in fact, that data, because it's redundant, makes self-supervised learning more efficient. So we have to crack that nut of being able to train systems to learn how the world works by watching video, like babies and like baby animals. We're not going to get to human-level AI by just training on text, which is why Ilya is wrong.
Yeah, so on that note, we know who you think are wrong. Who do you most align with? in today's leading researchers or academicians?
So,
It's all ending in friendship, right? not calling everyone it.
okay, so the story of my research career has been to attempt to align other people to my view. Okay, but you can't do this with self-respecting scientists. You can't tell them what to work on. You hire them because they have a good nose for what to work on, right? So, corralling scientists to a particular view is like cat herding. It doesn't work. Okay, you have to use reverse psychology or something. I mean, it's very difficult. Which is why, by the way, I'm not a manager anymore. I'm an individual contributor. I have the best job at Meta because I'm a senior VP, but I have nobody reporting to me. That's like the best position ever. But I have a little bit of legitimacy and intellectual impact, so when I say something, a few people listen to me. Not because they have to, because I'm their boss, but because they want to. And that's a much better position to be in. Okay, so now...
You should have to give a name or a couple of names.
Okay, so the people I like are mostly people who are interested in robotics, because when you work on robotics, you have to think about planning, reasoning, dealing with the complexity of the real world, all the problems that LLMs really are completely getting around. So I've been interested in robotics for about 20 years and working on various projects in the context of robotics. And I think the people who are bringing sort of new conceptual advances to machine learning are people who do basically, they call it model-based reinforcement learning. I don't like the term. I think it's more optimal control and combining this with machine learning. So there are people who basically try to use deep learning and apply it to robotics. So people like Sergey Levin at Berkeley, Peter Abil, Chelsea Finn at Stanford, Russ Tedrick at MIT. I mean, there's a bunch of people like that, and I think that's where the field should do more of that. I wrote a long paper that I put online 2.5 years ago. The title is A Path Towards Autonomous Machine Intelligence, and basically I explain where I think AI research should go over the next decade. And that's the plan that we're following at FAIR, and I hope to convince other people to help.
Cool. Thank you so much. And I couldn't take all the questions, so my apologies for those whose question was not taken. But thanks again, Yann, for being with us and taking all the questions and being your outspoken self. Hope Meta is not too angry with me or you.
Thank you, Gaurav. Thank you, everyone.